Welcome back guys to one of the most important lecture in this course, which I will talk about PID Controller. And actually in this lecture I'm going to explain the concept of PID Controller without talking much in mathematical details, so that you will enjoy the lecture, understand the concept of PID Controller and not get bored. So let's get started. As we have talked in previous lectures about any control system, we have what we call system or plant, and we have the mathematical equations of this plant. The plant produces controlled variable, so this variable is the one I want to control, or I want to make it reach to a certain value. And in order to make any control system, actually we take a feedback signal from this control variable and we feed it back to a summing point in which we have here commanded variable. And what is commanded variable? It's the variable that I want my output to reach. For example, if your planet is a mass spring damping system and you want your mass to reach 5 centimeters, for example, above the ground, so the commanded variable is 5 centimeters. You may design a controller that makes your system not reaching 5 centimeters, maybe for example 4.8 centimeters in a steady state response. So here we have what we call error. Error is commanded variable minus controlled variable, and actually we feed this error inside the controller. We design this controller in order to make our controlled variable reach the desired value. The output of this controller is actuating signal, and actuating signal enters the plant in order to control or to provide a control action to the controlled variable. One of the most important types of controller is what we call PID controller, or proportional integral derivative controller. And actually what we do in any controller is to analyze and use this error signal in order to provide an adequate actuating signal. So in PID controller we have here an input minus the output or the controlled variable, which provides error. Error is fed to 3 blocks. The first block is for proportional controller, and proportional controller have a constant Kp times the error signal. And also we have what we call integral controller. In integral controller we integrate the error signal, and we have derivative controller in which we differentiate the error signal. The 3 signals out of these 3 components are summing and provided to actuating signal. I don't want to talk in details about the mathematical foundation of the PID controller, but actually the most important concept I want you to get from this lecture is to understand what is meant by PID controller. So in order to explain this concept, we will look at drone controlling problem. So imagine that we have drone, and we want this drone to reach 50 meters above the ground. If we look at the drone, we will find that we have the weight of drone, which pulls the drone down, and in order for the drone to fly or hover, we need to provide a force from here. We found that forces that will be equilibrium with the weight and cancels the effect of weight is at 100 RPM, which means if this drone reaches, or the motors of this drone reaches 100 RPM, we will provide a force that cancels the weight of this drone, and at this moment the drone will hover. So we need this drone to reach 50 meters, and at this height hovers. So if we look at our control system, the plant here is the drone, and we have the mathematical equations of the drone. The desired output is reaching 50 meters. We want this drone to reach 50 meters and hover at this height. the actuating signal is propeller speed. So the output of this controller is the propeller speed. So we want this value to be at 100 RPM. And for example, we will try proportional controller. So we will use KP, and I will show you how to use different values of KP in order to track the response and error of this drone. So imagine that this drone at the ground. So in this case, the error is 50 minus 0, which is 50. Based on our controller design, we will find that the speed equals to error times the proportional controller constant. So for example, imagine that we have used KP equals to 2, and when the drone is in the ground, which means that the error is 50 minus 0, we will find that the speed of the motors equals to 50 times 2, which equals to 100 RPM. So in this case, the drone will hover in the ground. We may increase the value of KB to be, for example, 5. So in this case, the drone will go up until reaching height of 30 meters. The error in this case is 50 minus 30 equals to 20 meters. And the speed equals to 20 times the KB, which is 5, so equals to 100. So at this case, the drone will hover because we reached speed of 100 RPM, but we still have what we call a steady state error, which is 20. When increasing the value of KP, you will find that we have reduced the steady state error. But there is no way for this error to reach to 0 or to be eliminated for a very simple reason. If this error reaches to a 0 value, the speed of the drone will be 0, so the drone will be dropped from its height. So in many applications, when using proportional controllers, we will not remove what we call a steady state error. The problem now is we want to eliminate the steady state error. So imagine that we have added to our control design what we call integral controller. And the integral controller actually takes the error and integrates it over time to provide a control action. The derivative controller takes information from past because it integrates the error starting from the simulating time until reaching the desired output. So we always look about information from past. So it's like memory, it integrates error over time. So let's look at the drone problem again. Imagine that the drone has priced up. So we have here what we call the steady state error. The steady state error here is a non-zero value, which is constant value. So what integral controller do is when integrating non-zero value, we will have increasing action. So the drone speed will keep to increase until reaching to a point where the steady state error reached to 0. In this case, we are adding 0 to our problem, so the actuating signal will not change and the drone will be hover at 50 meters. So now we have managed to eliminate the steady state error. Now the question is, does this controller actually do what's supposed to do? Is it a good controller to consider? The answer is, it depends on your applications. And this example will tell you why. Imagine this case where we have a very small error in which we can consider the proportional controller is not working because we have an error which is very small that reaches to 0. So we have no control action from this proportional controller. But actually what we have here is the integral controller will keep summing the error over time, so that we will find that we are not reaching 100 RPM speed. We will pass this speed to another speed, for example 102. So what we have here is we have overshoot, or we have reached undesired value. So the drone now will not be at 50 meters, It will be, for example, above this 50 meters by a small amount, and will produce a negative error. This negative error is a must in order to integral controller to correct this action or this overshoot and get back to the steady state. So yes, we have eliminated the steady state error, but actually we have created what we call overshoot in order to get back to the steady state position. In some applications, overshooting is not a good thing. So, what is the solution to this problem? You need to upgrade your controller. We have added another term to our controller, which is derivative controller. And actually, derivative controller looks at future for a very simple reason. It differentiates the error over time. So imagine that the drone is moving up with very high speed. And actually what controllers see is that we have rate of change of error, or the error is decreasing with high rate of change. And by differentiating the error, we will reach to negative value of error, which is actually reducing the speed of the drone. So the drone will go up very speed until the derivative controller adds a control action, and the drone will go slow until reaching to 100 RPM and will hover at 50 meters. So actually we have managed to eliminate the oscillations and overshoot by using derivative controller. So now we have built what we call PID controller. A PID controller managed to eliminate the steady state error of this drone and actually to reach to fast response of this drone in order to move from the ground up to 50 meters without overshooting or oscillations. So in order to summarize what we have talked in this lecture, we have talked about three terms in PID controller. The proportional controller, and actually it doesn't eliminate the steady state error in most applications. And in real life, proportional controller always added with other controllers. High gain values reduces the steady state error but leads to some system oscillations. Integral plus proportional controller. The integral controller integrates the error signal over time. It manages to eliminate the steady state error, but unfortunately it adds overshoot, and in some systems it can lead to system instability. Derivative plus proportional controller. The derivative controller has high sensitivity, provides significant correction before the error becomes too large, doesn't affect the steady state error directly, adds damping to the system which eliminates or removes the overshoot.